Hi, my name is Ben. I'm going to talk a bit about Hochschild cohomology and how it relates to the fundamental group of a finite dimensional algebra. This is all joint work with Leonard Rubio Degrassi, my co-author, who is also giving one of these talks. And if you are thinking of watching both these talks, then I would watch his talk first because it might give some interesting context for what's going to happen next. But let's get started because we don't have too much time. So the setup is always the same. We're going to have some finite dimensional basic algebra over an algebraically closed field K. And in this case, we're going to be talking about the first Hochschild cohomology group, which you can just define to be the vector space of derivations on A modulo the inner derivations, or modulo all derivations of the form bracketing with some element. In that situation, this turns out to be a finite dimensional Lie algebra. So you can take two derivations and bracket them and get another derivation. So you have the structure of a Lie algebra. And various authors recently have been interested in what this Lie algebra looks like and what you can tell about it. And I will talk about that, the Lie theory of this thing. But first, let me point out that if you have a field of positive characteristic, then it turns out there is a little bit more structure here. This is a restricted Lie algebra, which means it has this p power operation on it, which is pretty transparent in this case. You just take a derivation and you raise it to the power p, so iterate it p times, and that turns out to be a derivation as well. And that gives you keeping track of that operation gives you what's called a restricted Lie algebra, that p power operation. And it turns out having that is actually quite important if you want to do certain types of Lie theory. You can get in trouble in positive characteristic if you don't have a restricted Lie algebra to study things like tori and stuff like that. So luckily we do, and we're going to be exploiting that later on. But let me just state this theorem that Leonard and I have, which is, okay, it says that among self-injective algebras, this restricted Lie algebra, HH1, is an invariant under stable equivalence of Morita type. So the key word here is restricted. The difficulty of this theorem is proving that, well, I'll say it here. So what it's saying is that if you have two self-injective algebras, A and B, and if their stable module categories are equivalent by a stable equivalence of Morita type, which means that there is a bimodule that induces this equivalence when you tensor over it. In that case, there is an isomorphism between the first Hochschild cohomology groups, and it respects the p power operation. So that's the hard part of this thing, to prove that it respects this p power operation. So the goal of this talk is for me to explain how we can exploit this by and what this has to do with something called the fundamental group of our algebra, with maybe some applications at the end. Okay, so I should first tell you what the fundamental group is. It begins with a quiver and some admissible ideal I in the path algebra. So in this situation, the path algebra has a basis of paths. That's not super surprising. And the ideal also has a basis of what are called minimal relations, which, so a minimal relation is you just write your relation as a linear combination of paths, all starting and ending at the same point. And this relation is called minimal as long as no subsum of it is also in the ideal. So just as long as it can't be split up into two sums, which are themselves relations. That's what being a minimal relation is. And you can give I the basis of such things. Having done so, you will say the two paths, Pi and Pj, are equivalent if they both occur together in some minimal relation. So they get identified if there's some minimal relation where they both live in there. The fundamental group is going to involve walks, so being able to go in both directions along a quiver. So we just say a walk on Q is a path in Q union Q inverse. So it's just saying you're allowed to go in both directions now. And up to this equivalence relation, saying firstly that if you go back and forth along an arrow, that should be the same as doing nothing. And secondly, that well, we incorporate this equivalence relation that if two arrows are equivalent, then they are still equivalent as walks. Okay. Having done this, one can define the fundamental group to be the set of all walks that go from a given vertex V to itself up to this relation here. So I haven't included a V in the notation here because this up to isomorphism doesn't depend on V. And that is our fundamental group. This was defined by Martinez, Villa, and Della Pena. And it turns out it works very much like the normal fundamental group that you might be used to from topology. It is a finitely generated group using just concatenation of loops. So that works quite well. I will just skip to giving you some examples of this so that we can get some idea of what's going on. First one, maybe the simplest situation is when you input a monomial ideal. Because in this case, what happens is the minimal relations are all paths. And if you think about it, the equivalence relation you get is then trivial. Paths only get like identified with themselves. So there's no interesting identifications. It only depends on the quiver. And the answer you get is just a free group on however many holes your quiver has in it. So it's the same as what would happen if you just took the topological fundamental group of the underlying topological space of your quiver. Let's do a more interesting example than that, though. Let's take this quiver, and firstly, let's put this relation on it. So just gamma alpha is 0. That one, that is a monomial, right? So in this case, we can just follow the previous example and say there's this hole here, and the fact that there's this hole here is going to tell us that the answer is the integers. Okay, let's do something non-monomial. If we identify these two top and bottom paths here, then the effect of that, if you work through the previous definition, is just to fill over this hole and identify that with itself, and then you end up with 0 as a fundamental group, and there's nothing here. Okay. Some of you may have noticed there is an issue with this already, which is that these two algebras are isomorphic. These two presentations define the same algebra. It's kind of a big problem if you're interested in invariance, right? Because the idea is to get stable invariance. That's kind of what this talk about, finding invariance under stable equivalence of Morita type. But this fundamental group doesn't even depend on A up to isomorphism. It depends on a choice of presentation of A. So this is kind of an interesting dilemma. So some authors, Sibley and Delamere and their co-authors have considered, they've tried to produce sort of canonical fundamental groups. Like if it depends on your choice of presentations, is there like a best presentation, or is there something else you can do to cook up the fundamental group? So our perspective is a bit different to this. What we want to just do is just, okay, there's lots of them. We're going to consider all of them. The totality of all different fundamentals groups you get over all different presentations, that is an invariant, because you're just throwing them all in there. So that's what we're going to do, and I'm going to show how that idea relates to tori in the first Hochschild cohomology. Okay, so you can talk about tori in any characteristic, but let me give you the characteristic P definition, because it manifestly involves this. This is what I was talking about, how using the restricted structure to talk about the Lie theory is important. So a torus is just an abelian Lie subalgebra, which is generated by elements that satisfy x to the p is equal to x, the p idempotent elements. So as a corollary of our theorem from above about invariance of this structure under stable equivalence of Morita type, tori, the set of all tori, is also invariant under stable equivalence of Morita type, because it's only using the bracket and the p-power operation, which is exactly what the theorem was saying, that these are invariants. Okay. So that means we can start freely talking about tori. Here is a theorem of Assam de la Peña and then of de la Peña and Saurin. They generalized it to include more algebras. So for any algebra with a presentation like this, you can take that fundamental group with respect to that presentation and dualize it, just take the group of characters, and it turns out there is a canonical embedding of that thing into the first Hochschild cohomology. And the image of this embedding is a torus inside here. So this is how tori are showing up from the fundamental groups. You start with some presentation, and it turns out this fundamental group, once you dualize it, embeds directly into Hochschild cohomology. It sits in there. So that's somewhat interesting. Maybe the first question one might have about this is, okay, which tori do you get then if you're seeing fundamental groups showing up as tori? If you want to do this sort of intrinsically without a priori knowing much about A. And Lemurre was interested in this. It turns out you get all maximal tori in these two cases. So if you have a characteristic 0 with no double bypasses, or if you have a monomial algebra with no parallel arrows and oriented cycles, it's true. So I'll skip to the main theorem. The main result is that actually this is just always true for any algebras. So for any finite dimensional basic algebra A, all the maximal tori in HH1 are of the form sigma of some dual fundamental group. So every maximal torus occurs from some fundamental group in this way for some choice of presentation. So as a corollary of this, these are all like immediately stable invariants. So among self-injective algebras, the maximum rank you get of these things, which is the toroidal rank of this Lie algebra, is an invariant under stable equivalence of Morita type. For monomial algebras, we already talked about how this is just the number of holes in the graph, which you can write like this, the number of connected components minus the number of vertices plus the number of arrows. And let's say for self-injective algebras are the number of holes is an invariant under stable equivalent Morita type. And in particular, it's also true for derived invariance, because a derived equivalence gives you a stable equivalence Morita type. And for derived invariance, these two things here are themselves invariants. And that tells you that this thing here, this remaining thing, the number of arrows, for self-injective monomial algebras, the number of arrows is a derived invariant. This was proven by Alamenius and Geis for gentle algebras in 2007. Okay, so I have to stop. I don't want to run over, so I will stop there. Thank you, everyone. Thank you.